Alright. We're almost done. Second to last question for this chapter. But of course it has to be an obnoxiously long question. But a very interesting result. And this is a very good question that gets you ready for what you're going to see in chapter 8. So let's dive in. So prove 𝘰𝘮𝑗's theorem. I don't know if I'm saying that right. In a perfectly conducting fluid, say a gas of free electrons, the magnetic flux through any closed loop moving with the fluid is constant in time. The magnetic field lines are, as it were, quote, frozen in the fluid. A. Use Ohm's law in the form of J equals sigma times E plus V cross B, together with Faraday's law to prove that if sigma is infinity, conductivity is infinite, then and J is finite, then the time derivative of B is equal to the curl of V cross B. Alright, B, let S be the surface bounded by the loop P at time t, and S prime be a surface bounded by the loop in its new position P prime at time t plus dt. See diagram. Alright. So, the change in flux is dphi. Okay, I'll just let you read through this because this is in the book. This is what they're giving you to try to start the problem. So I'll give you a moment to read over that. I'll go over it in more depth when we see it in the actual practice here. But this is all part of the statement. You can pause the video here if you want to read it more. But I'm going to go to the diagram. You see here that we have some surface S bounded by P, and then translated by R to some prime coordinates via V dt. S prime and P prime, and from this let's go ahead, and then R forms that quote ribbon. Let's go ahead and start tackling this question then. So if J is finite and phi, or the conductivity, is infinite, then we see that the E plus V cross B has to equal 0. Okay, there's really no such thing to deal with there, since J is finite and the conductivity is infinite. If we divide it, then we see that we have J over sigma, and anything divided by infinity goes to 0, so that makes sense. Well, not anything, but in this case, a finite divided by infinity goes to 0. Alright, so if we take the curl of both sides, what we see is the curl of E plus the curl of V cross B is equal to the curl of 0. Of course, the derivative of 0 is 0. No big deal. But Faraday's law tells us that the curl of E is equal to negative B dt, so we have all this equal to 0, and the curl of V cross B is equal to 0. So therefore, the curl of V cross B is equal to dB dt. That's pretty easy, pretty fun to see actually. Now let's get to work in. So in part B, starting with the fact that the divergence of B is 0, we know that the surface integral of B is equal to 0 too. Okay, or the flux integral. So we got to be careful here for any closed surface. And the reason why we have to be careful is we have to apply this very strategically. Okay, so knowing that this thing equals 0, we can define the field at time t and t plus dt to the surface consisting of S, S prime, and R. Alright, what we mean by this is, with all that being said, since this is a closed integral, okay, the closed surface, okay, we need an integral with S prime, R, and S. Okay, with that being said, the surface from the diagram, S, okay, has to be equal to, the closed surface is S prime plus R minus S, since we're translated. Okay, that's what the whole thing is starting with. And this is at t, d equals 0, or b at t plus dt, okay? So this is at some later time, but you see the minus sign here comes from the orientation of S with respect to where we are at S prime and R. Okay, so that's going to be opposite since it's at some later time, and we're just going to have to flip it. Okay, well, now with this integral equation, what we need to do is show that we need to solve this for S prime, and then we can plug in things that we know from other equations. So that's why I color-coded it this way. If, for instance, we take and we add over the S surface and we minus the R surface, then we can solve this for the S prime surface. All right. So again, like I said, the sign change in the third term comes from switching dA from outward to inward. Okay, so don't be alarmed of anything. That's just how we deal with it. So what we're saying now is that the change in flux, okay, which was equal to, remember that flux was equal to the area integral, okay? Now this is different from the closed integral. The flux integral is just the area integral, but we have two areas to consider here, the S area and the S prime area. So the S prime belongs to the B plus dt field, and the S belongs to the BT field. Okay, but notice how the two of them, the change of it, they have to combat each other. So the flux at some later time dt minus the flux at the beginning time is equal to the change in flux. And that's what we see here. But notice that we saw from the divergence equation what this red integral is, the S prime integral, and we can substitute it into the change in flux. Okay, so this is the step that makes it all work, and we need to just play with it a little more. All right, so with this, we see that we have a surface integral on S, a surface integral on R, and then we have minus another integral on S, B dot dA. Okay, again, this is how the change in flux would be calculated. Now, what we need to do here is we see that we can combine the integrals that have the same surface S. Okay, so that's B t plus dt minus bt. Okay, dot it with dA. And then here, for the ribbon R, our dA is pointing outward or pointing differently than the dA that we have in the S surface. Okay. So in the next step, what we're going to do is consolidate the B t plus dt minus bt into this equation, which is the partial of b times dt for some infinitesimal dt, okay? That's literally just saying the difference. If you go back to the derivative, that's just the difference, okay? But again, it's a difference only with respect to t, and that's how we condense that. All right, so furthermore, yeah, okay, that should just be, yeah. And then we see here that the dA on the R integral turns into dl cross v dt. Kind of makes sense because it needs to be perpendicular to R, which is equal to v dt, because R is the ribbon length that is running. So dl cross v gives us perpendicular. So now we're set up pretty nice. So here, now we can kind of factor that dt out from the from both of these integrals, and the S integral becomes, or the change in flux for the S integral becomes partial d b dt over dt dot dA times dt minus the R integral b plus t dot b of t plus dt dot dl cross v, all with respect to t. Since the second term is already first order in dt, we can replace b of t plus dt by b of t, meaning that since we're subbing in for the little change in displacement of dt, we don't have to write b of t plus dt, so that's why we make that change. And what this allows us to do here is factor in a little bit different here. So we factor out the dA or the dt's for both of them, and we see that the S integral is to stay the same. But since we have this here, we are trying to change the R integral to a closed integral via the one of the theorems. And yeah, because we can change the order here of integration. Yeah, by moving it to a closed path, so V cross BT. So that took a couple steps to show, but be aware that it is okay. Those are just vector identities, and we're trying to get DL by itself, so V cross B. Okay, so I believe Stokes' theorem can help you with that. And then, yeah, keep plugging it through, because now from Stokes going backwards from the closed integral, we can go back to the Stokes' theorem of the S integral, and we can write that the curl of V cross B dot dA from the line integral above, And we can see that the change of flux with respect to time is equal to everything on the S, partial BT divided by partial T minus the curl of V cross BT dot dA. Alright, so that's actually pretty cool. But be aware that the vector identities will change and will come into play as we move things through. We see that, again, with these movements, you got to use the theorems and vector identities. They're going to get messy, but this one's fun.